In this lecture, we'll be going over the solution of a constrained optimization problem regarding the first-order necessary conditions for a local solution, namely the KKT conditions. So recall, this is our framework. We're minimizing over x vectors in Rn. The objective f of x such that we have a set of equality constraints satisfied, indexed by I in the index set E, and a set of inequality constraints satisfied, indexed by I in the index set script I. To do so, we build this Lagrangian, which is this new function, which has both x and a vector of Lagrange multipliers lambda as the variables. We see here f of x is the objective, and then we are subtracting a Lagrange multiplier lambda I times the constraint expression c sub I of x for each of the constraints, both equality and inequality. The first order necessary conditions for a local solution, feasible local minimizer, are these KKT conditions, the Karush-Tucker conditions. So suppose x star is a local solution of our optimization problem, summarized here. And then we have the linear independence constraint qualification, LICQ, holding at x star. Then there exists a Lagrange multiplier vector lambda star with components lambda I star, one for each of the constraints, such that the following conditions hold at x star lambda star. So first, the gradient of the Lagrangian function with respect to x equals the zero vector. We have feasibility, so all of the equality constraints are satisfied at x star. All of the inequality constraints are satisfied at x star. And then we have each Lagrange multiplier greater than or equal to 0 for all of the inequality constraints. And then finally, we have what we call our complementarity condition, that one of lambda I star or ci of x star equals 0 for all of the constraints. And this complementarity condition, the product being 0, is what forces one of them, at least one of them, to always be 0. So we're going to look at the following example. So we're minimizing the quantity x1 minus 3/2 squared plus the quantity x2 minus 1/8 to the fourth with this set of inequality constraints. And we know that that set of inequality constraints results in the feasible region of this diamond here in the x1, x2 plane. And we note that the global minimum of f in the unconstrained sense occurs here at the point 3/2, 1/8. And we can see that because we note that each one of these terms in parentheses, they're both raised to even powers. So the smallest, the first term here could be is 0, which occurs at x1 is 3/2. And the smallest, the second term could be, is also 0, which occurs at x2 equals 1/8. So we know that this objective function has an unconstrained minimizer at the point 3/2, 1/8. But we want to know what is its minimizer when restricted to the interior and the boundary of this diamond. It helps to look at the function. So here in the x1, x2 plane is our feasible region, and this upward opening convex paraboloid is our objective function, and we're minimizing this objective function above this region omega. So the graph of the lowest point of the graph of this function f above this little diamond here. And we can see visually, we're going to guess that that occurs at this right-handmost point. And so just visually, we're guessing that that is actually the point at which the minimum occurs over the feasible region.
Looking at the graph in Desmos, we can see here the orange point is our optimal point, 1, 0 in the x1, x2 plane. The gray diamond is our feasible region, and this blue surface is our objective function restricted to the feasible set. And we do see that its lowest point occurs above this point 1, 0 right here.
Another way we could figure this out is we could try contours. We could try level curves of the objective function. So recall what that means. You take the objective function and you set it equal to a constant, and then you try different constant values. This is the idea of, say, a contour map. If you set this equal to 4, we will draw a curve in the x1, x2 plane, and on that curve, f of x is always equal to 4. In this case, when we do that, we get ellipses centered at the point 3/2, 1/8. These are small values, 0.01, 0.05 for A. And as we increase those, the ellipses are getting larger and larger. We want to increase A until we get to the smallest value of A, where we just intersect the feasible region. And that happens at this point 1, 0. So this is the lowest level curve, such that we actually get that intersection. So we see here that this point 0, 1, 0 is in fact our local solution to the problem. And what we want to do now is work this out with the KKT conditions. So there will be a corresponding Lagrange multiplier vector lambda that couples with this solution, satisfying all of the KKT conditions. So the first thing we want to recognize is which constraints are active and which are inactive. And they're labeled here, but recall that active means the point x star is on the constraint boundary. So this constraint here is our C1, the first of our constraints. So C1 is active, and this constraint here is C2. So C2 is also active. We can see that constraint C3 and C4 are inactive because while the constraints are satisfied, this point is not on the constraint boundary for those two constraints. So because C1 and C2 are active and C3 and C4 are inactive, we can garner some information about the Lagrange multipliers. Before we do that, let's start to set up our problem. And the first thing we need to do is to get all of our gradients in order, because we need all of our gradients for the gradient of the Lagrangian, the first of the KKT conditions. So what we've done here is we've taken the partial derivative of f with respect to x1, and we get 2x1 minus 3. And we take the partial derivative of this f with respect to x2, and we get 4 times the quantity x2 minus an eighth cubed. Those two give us the components of our gradient of f. And then we are going to evaluate the gradient of f at x star, and recall x star is the point 1, 0. So plugging in 1, 0, we get a minus 1 in the first entry, and 4 times negative an eighth cubed, which is minus 1 over 28. So this is our gradient of f evaluated at the local minimizer x star. And then when we take the gradients of each of our components of our c vector, you see here the gradient of this first c1 would be partial with respect to x1, which is minus 1. Partial with respect to x2, which is minus 1. And then notice x doesn't show up in here, so the gradient of c1 at x star is just negative 1, 1. And we get similar gradients in each case. Summarized here, we have everything we need for that first condition. Again, the gradient with respect to x of the Lagrangian being equal to 0. That was what we called KKT condition A. Now let's come back to our active and inactive constraints. So remember that C1 is active and C2 is active. So what does that tell us about the Lagrange multipliers? Remember that the idea of this complementarity condition really is that you can treat the Lagrange multiplier like an on-off switch. If C1 is active, its Lagrange multiplier is on, meaning it's positive. If C1 is active, C1 of x star is equal to 0. Since C1 of x star is equal to 0, that allows that lambda 1 star to be positive. We have the same result here. C2 of x star being active means that it holds with equality. Remember that each of these are inequality constraints, but being active means they hold with equality. And so their Lagrange multipliers are on. Since C3 and C4 are inactive, C3 at x star was strictly greater than 0, and this complementarity condition requires lambda 3 to be 0, and the same for lambda 4. C4 of x star, it's not binding or inactive. And so we require to have complementarity lambda 4 equals 0. And this means we've already solved for 2 of the entries in our optimal Lagrange multiplier vector. We know that lambda 3 star and lambda 4 star are both 0. We have here. Let's come back to our gradient condition. So recall, we had just said that KKT condition A has that the gradient of the Lagrangian with respect to x has to be 0. So if we calculate the gradient of the Lagrangian, here's our Lagrangian here, with respect to x, well, the gradient with respect to x of f of x is simply the gradient of f of x. Then we have lambda I is a constant. Gradient with respect to x of each ci of x is just the gradient of ci of x. So KKT condition A, specifying that this is equal to 0, means that the gradient of f of x star is equal to the sum I going from 1 to 4 of lambda I star times the gradient of ci of x star. But note, lambda 3 star and lambda 4 star were 0. So the third and fourth terms in this sum are 0 because the lambda 3 0 wipes out the term and the lambda 4 0 wipes out the term. So this becomes the gradient of f at x star is the sum I ranging from 1 to 2 of lambda I star gradient of ci at x star. Or the gradient of f at x star is lambda 1 star times the gradient of C1 of x star plus lambda 2 star times the gradient of C2 at x star. We're getting this from the KKT condition A, and we're factoring in the information that we garnered from our solution guess and what it said in terms of complementarity about these two Lagrange multipliers. Putting this together, this is the equation that we had just written down before, and here we are plugging in. So here we have our gradient of f, lambda 1 star times the gradient of C1 at x star plus lambda 2 star times the gradient of C2 at x star. Here we plug in, remember, x star was 1, 0, so we plug in 1 for x1 star and 0 for x2 star, and that gives us negative 1 and negative 1 over 128 for the left here. And this is now a system of two equations and two unknowns. And so we want to now solve this system for lambda 1 star and lambda 2 star. So writing them down as equations, we would have this, and then we can do our however you want to solve this type of equation, we can say from this first equation, lambda 1 star equals 1 minus lambda 2 star. And then you could plug this in to this lambda 1 star here and solve. And when you do that, you get lambda 1 star is 127 over 56, and lambda 2 star is 129 over 56. And putting all of this together, we now have our solution. So we have the solution x star is 1, 0, and lambda star is 127 over 256, 129 over 256, 0, 0. And these collectively satisfy the KKT conditions. So to be specific, the gradient with respect to x of the Lagrangian is equal to the 0 vector at these values. Ci, we have no equality constraints, so 2 is trivially satisfied. 3 is satisfied from the way that we derived things. We are at a feasible point. We can read right off the vector that all of our lambda I stars are greater than or equal to 0 for the inequality constraints, or all inequality constraints in this case. And we also have complementarity, because C1 of x star was binding and C2 of x star was binding. When we multiply C1 of x star times lambda 1, we get 0. When we multiply C2 of x star times lambda 2, we get 0. So we do see that these conditions are all satisfied, and this gives us a confirmation that it was, in fact, at this point here, which was 1, 0 in the x1, x2 plane. If we look up from there, whatever that function value is here is the lowest point. And to get that function value, you can, of course, evaluate the function at 1, 0. We know the function was x1 minus 3 halves quantity squared plus x2 minus 1/8 quantity to the 4th. And if we plug in 1, 0, which we know satisfies the KKT conditions, we have 1 minus 3 halves is negative 1/2 squared plus 0 minus 1/8, so minus 1/8 to the 4th. The minimum value of f over that feasible region, omega. Now we know from this problem, this is a convex problem. We know with convexity things are much more straightforward in terms of finding a local solution. But if we didn't have convexity, we would have to look to second order information to determine that this is in fact a local minimizer, and that will come in a later lecture.